Hello everyone, so thank you for attending to this talk. I'm Roman Thomas, I'm security engineer at Quarks Lab, where I'm in the team that performs security assessment but also develop tools to automate the reverse engineering process. And among these tools we develop Triton, which is a symbolic execution framework. We also develop Leaf, which enable to modify executable formats such as ELF or PE. And we developed QBDI, which is a dynamic instrumentation framework that will be discussed in this presentation. So this talk is about Android obfuscation and how we can analyze obfuscation using dynamic instrumentation framework. So obfuscation is a way to protect application asset against reverse engineering by making analyzing more difficult or at least very time consuming. And obfuscation can protect different kind of asset. So it can be like a function that we don't want to be reversed. It can be a file that we don't want to extract from the application, or it could be a secret such as a token or a password. So to protect and to make obfuscation, there are different solutions. So there are commercial one with Arxan, Clockware, or Epona. Some app developers also use in-house obfuscator, which is the case for Snapchat or TikTok. And there are some open source projects such as OLLVM or Ikari. So this topic is not new, and there are a lot of presentation and paper about this topic. Especially in 2014, two former colleagues of Quarks Lab presented some work on attacking white box with using auxiliary attacks. So it were basically using dynamic trace, and they show how they managed to break the white box using dynamic trace generated by Intel pin. In 2016, Charles Heuben and Philip Towen presented some work also on attacking white box using dynamic trace, and they show how we can use side channel attack with this trace on the white box to recover the cryptographic key. And last year there were a presentation on reverse engineering C++ code and how we can use dynamic information to recover internal structure of internal field of C++ structure. From this research, we can see that basically a DBI is suitable to address obfuscation because it provides dynamic information, and somehow dynamic information can't lie, and we'll see how. So a DBI is a way to analyze a program dynamically at different levels. So you can analyze the program at instruction level. So for instance, you can access to all the instructions that are executed for one execution path. You can also access to register value. You may also access to the basic blocks that are executed. So you have different level of analysis over the program. And while a debugger will insert breakpoint before each instruction to have access to the underlying instruction, a DBI will modify the assembly code and will execute the modified version of the assembly code. So in terms of performances, you are more efficient with a DBI than with the debugger. And if you want to analyze, for instance, a lot of instruction, you may pay a very huge overhead with a debugger, while with a DBI it can be like very quick. So there are different frameworks to do that. The first one is Intel pin, which is quite well known now. And it works very well on x86 and x86-64. You may also heard about Valgrind, which enable to instrument code on the 4 architecture. But I would say that the DIPI is not very convenient if you want to select, for instance, a specific part of the program that you want to instrument. There are also dinamorio and din-ins, which I don't know if they really support RAM and RAM64, or at least the API is not, the support is not very full. And we have Frida, which also enable to trust instruction for the 4 architecture. And you can trust instruction with Frida thanks to the Stalker. And we develop also QBDI, and we'll see how QBDI address different functionality from the previous framework that we mentioned. So a bit of history of QBDI. So the project started in 2015 by Charles Heuben and Cédric Tessier. In 2017, they presented the project at CCC. And in 2019, I added the support for RAM and RAM64. And in the next few months, Paul, one of my colleagues, presented some work on using QBDI to perform fuzzing with OnFuzz. In 2020, we started to integrate some tools with QBDI, such as Frida or Binary Ninja. So QBDI were created by Charles Heuben and Cédric Tessier, which are 2 reverse engineers with a strong background in obfuscation. Especially Charles Heuben was one of the co-authors of the paper about attacking white box. This is why there are some functionality in QBDI that aim to target this kind of protection, and we'll see this functionality. The tool is based on LLVM. So LLVM is very, very handy because you have a disassembler, you have also an assembler, and you have an interface through LLVM MC inst over the instruction, regardless the architecture. So it means that you can access to the semantic of an instruction thanks to the abstract layer. So for instance, if you want to perform some, I would say, modification on a call, you can just query the mth-ins interface, and there you will have some information independently from the architecture. So the public version supports x86 and x86-64. In the private branch, we have the RAM and the RAM64 support. You may also find some piece of code about RAM support in the public branch, so it works quite well for non-thumb instruction, but for thumb and thumb2 it can be like tricky to work. Also, the project is available on GitHub, so feel free to check it if you are interested in. So let's consider this piece of code. So here you have a basic block that you want to analyze. So with QBDI, we will set up some callback before all the instruction by using the add code callback method. Doing so will set up some callbacks that will process the instruction, and for instance, you can analyze the register within this callback. And from a logical point of view, it gives you this figure. So here is the original code, and here you have your callback in which you can read the register, modify the register, skip the instruction, and so on. But obfuscators are likely to add noisy instruction. So for instance, if they are doing some computation that are not in the original code, it will add a lot of instructions that are not really relevant to understand the function logic. Also, if you try to instrument all the instruction, you can pay a very huge overhead, because if the obfuscator add new instructions, so it means that you will have to instrument and to switch between the original code and your callback a lot of time. So we need to be a bit smart if we want to scale with the DBI. So this is why there is some functionality in QBDI that enable to select a subset of instruction to instrument. So for instance, you can say, I'm only interested in instrumenting branch instruction, or I'm only interested in instrumenting memory access instruction or syscall, and so on. And doing so with this API, you can say, okay, so let's set up a callback on the syscall, let's set up a callback on the call instruction, and let's set up a callback on memory read or write access. You can also select memory read if you want, or memory write. And then you will only have callback before the instruction you select through the API. And you don't pay for the overhead for the other instruction. In addition, QBI have interesting functionalities that enable to resolve the effective memory address of instruction. So for instance, if you have a load R0 from R5, you have an API to automatically know the value of R5. But if you have, for instance, R1 and R6, it will automatically compute the value of R1 plus R6. And this is done in the API, so you have an abstraction over this computation. Especially if you have, for instance, this kind of memory access, it can be like quite tricky to compute. So here you just have to access to the access address attribute of the memory access structure, and you get the computation for free. You can also access to the effective value that is read or written through the value attribute. So here, for instance, you get the value of R2 and you get the value of R0 plus 18. We have the same mechanism for branch instruction, so BLX, BL for RAM, or BR and BLR for RAM64. And basically, if, for instance, you want to know the value of R2 associated with this branch, you can just access to this value through the install access and back. And then here you have the effective value. This is quite, I would say, simple for RAM64, but for RAM you have some tricky computation because of the thumb mode and some alignment computation. So here, for instance, for RAM instruction, it will automatically compute the value with the thumb bit. Also, another issue and another problem with DBI is how you manage to trace malloc, or how you handle malloc and external function when you trace code. So one of the issues with malloc, for instance, is that malloc may share some global variable with QBDI. So QBDI use malloc. So if your code that you trace use malloc and that malloc is traced by QBDI, you have like you can have an issue. And Intel Pin, for instance, choose to provide their own implementation of malloc, printf, and so on, so that there is no conflict between QBDI within the DBI, and the instrumented code. Also, in Android application, you can have a function that use GNI, which are basically functions that makes a bridge between native code and Java code. And you don't want necessarily to trace this instruction because you know the behavior of malloc. Malloc is allocating a buffer, so you don't want necessarily to trace these functions. So there is a way in QBDI to process this function by stopping the instrumentation process when there is an external call. Then we leave the function to execute their own code without instrumentation. So we are quite blunt about what the code is executed, but as we know that is malloc, we know the behavior of malloc. And QBDI also change the return value of the return address of the function so that we can catch when the function returns. So this diagram summarizes a bit of the process when there is an external call. So here, at some point in the instrumented code, we have a branch to malloc. So here, QBDI is able to detect that the absolute address of the branch is not in the part of the instrumented range. So we don't want to instrument the code at this address. So QBDI will just say, I'm stopping the instrumentation by triggering this event. Since we are in the process, we can resolve the base address associated with this absolute address. So as we have access to the memory layout of the process, we can also resolve the library in which this address is located. So we have both the library and the base address. So we can have the symbol offset. So here is the offset of the symbol within the library, and using an ELF parser, we can have access to the effective symbols associated with the offset. And then we can see that this absolute address is associated with malloc. Then we have the code that is executed, and when the function finishes, QBI changes the return address so that is able to detect when the function finished, and will trigger another event that is exec transfer return, and will resume the instrumentation until this point. And then we'll do the same mechanism. So with the exec broker, you are able to trace external call, and if the external call is done to a library, you may also resolve the symbol associated with the external call. Regarding GNI function, we can use the same mechanism. So GNI function is located in a structure, so it's basically a structure of pointer. And this structure is usually stored in the GNI env variable. So if you have access to this variable, you may compare the external address against one of the functions within this structure. So if here your absolute address match, for instance, find class, you can process the parameter in a dedicated callback. So here is an example that is typically used by GNI function when calling GNI function. So first it loads the address of the find class into R2, but you don't know that is find class. Then there is a BLX R2, which is a call to an external function. So the exec broker detects that there is an external call. From this point, you can convert this address into a symbol, because find class, you can resolve find class thanks to the env variable, and you can process the parameter. Then it's the find class function is executed. The exec broker detects that the function finished, and you can do the same analysis when the function returns. Especially, you can, for instance, analyze the return value. And doing so, you can have pre and post callback over the external function, which enable to analyze the parameter of the function and the return value. And this approach is quite interesting, because if you are using hooking, you must know beforehand which function you want to hook. But here, we don't know beforehand which function will be hooked. We just see that there is an external call, and then we resolve the external call into a symbol. And if we take strlen, for instance, we have a branch to, so here it's PLT-got code. We have a branch to this register, then there is an exec broker. We convert this absolute address into a symbol, then we process the parameter, then the function is executed in the libc, then the exec broker detects that the function finished, and so on. So to summarize, QBI provides some primitive to instrument code. So among these primitives, you can generate instruction trace, which is sometimes it's you need to have the information about all the instruction, but you can also have memory trace if you are only interested in memory access, or you can have syscall trace, or you can have internal call trace, or external library call trace. So this is what QBI provide. And when you have to analyze obfuscated code, you can use one, or you can combine this primitive. And now we'll see how we can combine this primitive to analyze obfuscated code. So one of the first configurations that we can use to address obfuscated code is to set up a syscall callback, because sometimes obfuscator try to inline syscall function so that you can do, for instance, hooking. But since you are since you have QBDI, you can have callback on syscall and it's okay. You can also set up the exec broker so that you get an external call trace, which is like strace, but for all the external functions, which is quite convenient. And you can resolve the external call into a symbol and process the parameter and the return value into dedicated callback. And you get a call trace. So here is an example. So in this case of protected code, we have the R2 register that is set by loading a value from the stack, and then we have a BLX R2. And if you try statically to reverse and to resolve the effective value of R2, it can be very complicated because it's coming from the stack and you need to track what the value at this offset contain and so on. But dynamically, you just have to set up a callback before BLX R2, and thanks to the abstraction in QBDI, you can just query for the call address, and then you get the effective address being called, which is here in this case in the text segment. So this is the kind of way to resolve indirect call. Another interesting configuration is to set up pre and post call callback, and within the call to record only the byte memory access that are printable. This is quite interesting because we can, in this configuration, detect functions that are decoding or encoding strings. If we take this example, so here you have a callback with QBDI before this call, and you have a callback after this call. Within the call, you will record only memory access that are done on a byte. So here, there is a loading byte. They are doing some computation and they are writing byte. This is a pattern that you can find in decoding string function, because usually obfuscator must be able to decode any string, and one way is to load a byte from a buffer to decode the byte and to write the byte into another buffer that will contain the plain string. And if we have at the beginning this kind of input that is loaded, here we'll find some decoding string, because here at some point the program needs the plain string. So at some point we'll find the clear string into a buffer, and using the memory access callback, you can find this string. Here is another example where we have a buffer here that is decoded using this algorithm. So this algorithm is, we can reverse this algorithm, we'll see just after, but let's say that it's very, very complicated and it's too much complicated to be reversed. Here, we just record the byte memory access, so we can see that it's reading this byte, which are this byte, but only the printable character. And we can see that within this function, they are writing def socket QEMU. So it's basically a function, string that is involved in emulator detection. Then here we can see also that we have a syscall that is detected with QBDI. And just by looking at the dynamic trace, we can avoid to reverse this algorithm. We just have access to the memory buffer that is read and written, and here we can clearly see the string that are decoded. But if you want to reverse statically the function, you can have a Python script that is doing basically the same thing. So we can confirm that we effectively managed to reverse the decoding function. Another interesting configuration is to track memory access, such as malloc or calloc, or if you are in C++ operator new. We can also track memory map functions, such as mmap. And when a code tries to dynamically allocate code, you can have a callback over this function and automatically update the instrumented range of QBDI so that the new code that is allocated will be instrumented. And when there is a free function that is called by the program, since you manage to intercept the malloc and all the dynamic memory buffer allocation, you know the size of the buffer that is deallocated at the end. So you can print the buffer being free. And we'll see an example right now. So here is a piece of code on mmap. So when the obfuscated code tries to dynamically allocate code, we can just take the parameters, and in the QBDI API, we have a function that enables to automatically update the instrumented range. And here we just say, now I want to instrument the code that is dynamically allocated through mmap. And here we have the API with the exec broker, so if you want to take a look. And here is what kind of output you can have with this configuration. So here we can say that the code is calling mmap, and here we have the address of mmap. Since we instrument the code, we can automatically update QBDI to instrument this new range of code. And here we can see that we have an mprotect that is setting the protect execute flag on the new instrumented range. And at the end, we have the mmap function. So here you get this kind of output with this setup. Now I'll go through a real use case and some example of using QBDI on Android application. So for this example, I took two obfuscators which are blue and green. The first example will be about GNI onload. So in Java, you can declare native function so that the implementation of this function is located in a native library. So here, if you want to understand the behavior of the function A, you need to first find the library in which A is implemented, and then you need to reverse assembly code. So this is the output, the control flow graph of the library associated with the GNI function. You can notice that you only have one export, which is GNI onload, and we'll see that GNI onload is basically the function that is doing the resolution between the declaration in Java and the offset in the library. And here is the CFG, which is obfuscated, so it's using control flow flattening. And if you want to understand how this sequence of basic blocks is executed, it can be like very, very painful. So in the GNI onload function, you have one specific GNI function, which is register native. And the purpose of register native is to bind an offset in the library with the declaration in Java. So by calling register native, you have a bridge between the native implementation and the Java declaration. So when the Java code will call the function A, it will actually code the function at this location in the library. So at some point, if you manage to catch register native, you can automatically resolve the offset of the function within the library. So using QBDI and the exec broker, it's quite straightforward because at some point there will be an external call. And because there is an external call, you can use the exec broker to resolve the function, the address into a symbol. And as you may know that it's register native, you can inspect the second parameter that contains the mapping between the function and the offset. And then you have access to the offset of the library. So here you can just go through this function and then continue the analysis since you manage to resolve the offset. So here is the basic block involved in register native. we can see here that register native is done at this address, and we can see that this address is actually here. So we can see that it's BLX R5. We don't really care about what is the value of R5. We just know that it's an external call, and here statically it could be like very complicated and tricky to resolve R5, so that here it's very straightforward. And here is another view of the same GNI of node function. If you are interested in a full demonstration of the dynamic trash generated by QBDI, you can check this video. So now let's move to another example which involves video game protection. So in a video game, you have similar threads as desktop games. So basically, you may want to modify the memory, you may want to dynamically modify the behavior of the game. And one of the well-known tool to do that is Frida, because the API is very, very simple, it works very well and fun. So one of the protections that are provided by Obfuscator is also a way to detect Frida, or at least to try to make Frida not run. And one of the video games that we analyze implement Frida detection, which are based on detecting TCP port. And because we don't want to have the protection within a single function that could be like hooked with Frida and change, they inline all the instructions through syscall that are involved in the detection. But thanks to QBDI, we can trust syscall. So we can identify where are the syscall, and we'll see how we can remove the protection. So here is an example of truss that you get with QBDI, and you can see that you have a syscall at this address, so it's trying to open a socket, then they are doing some bind functionality to try to open on a specific port, which is the Frida port, and then if he managed to open the socket, it will crash the game. And basically, one of the weakest of the protection is that when Frida were running, the game were crashing. And because it were crashing, we got a stack trace. And using the stack trace, we can identify which function crashed, and then we can say, okay, with QBDI, we want to trust this function to see what is the issue. And then we get this kind of output. So here is the static code associated with the function. So we can see that we have the syscall at this address, which is fine. And now that we managed to identify the syscall, we can use leaf to patch the syscall with the value -1, which stands for an error. So since we managed to identify the syscall, we can just remove this syscall with a wrong value. And now we just have the syscall, and we return -1 with the modification. And at the end, we managed to execute the game with Frida without issue. One of the limitations of this approach is that you need to identify all the syscall. And since you are only generate a trace for one execution path, you may not cover all the syscall. So you need to find a way to have a very good coverage over the execution path. Another example is within MDM solution. So MDM solution aims to provide a control over a set of devices that are deployed within a company. And basically, there is an admin user that is able to control, for instance, which packages are allowed to be installed on the device, which are not, and so on. And one of the features that are in this solution is to be able to detect if the device is rooted or jailbroken. Because if the device, for instance, is rooted, it's quite straightforward to bypass all the protection. So this is one of the key points in this solution if they want to be working quite well. But if you want to detect that a device is rooted, you need to interact at some point with the system. And since you are not able to link statically the libc in Android, you must call external function. And even though the original parameters are protected or the string are protected and so on, at some point the external call must be done with original strings. And the solutions that we analyzed were written in C++, and the wall were protected by the second obfuscator. And one tricky point in C++ is that you can have implicit destructor. So let's consider this piece of code. Here you have a string object within the check root function. Here you get a reference over all the characters located in string. You are decoding the string with XOR operation. And here at the end, you have a free memory. You delete the buffer allocated with string. But you don't need to write this piece of code. It's the compiler that automatically generates this call. And because you are deleting a buffer, at the end, your string variable contains the plain string. And with QBDI, you are able to detect when the string object is allocated, and you are also able to detect when there is an external call to operator delete. And you can just look at what the buffer contains, since you are able to know the size of the buffer and when it is delayed. And then you get this kind of output. And here you have all the checks that are done by the MDN within this function, which would be like very painful to analyze, but just by looking at the delete operator and looking at the buffer, you may know how the root detection is performed. Then you may want to identify where they are really used and so on, but at least you know what kind of check are done. I won't go through the detail of the Android packer, but we published a blog post about the reverse engineering of a packer, as well as the code to automatically unpack the packer. And if you are interested in how we did that with QBDI, you can also check this second demo. So 3 points to keep in mind when you deal with obfuscation. First, the obfuscator can break all the program semantic. It means that if the original code performs a syscall, you may have a syscall at the end. If there is some external call, the parameter of the external call can't be obfuscated. For instance, you can't obfuscate the string going through strlen. You can't obfuscate the buffer allocated with malloc. I mean, you can't obfuscate the size of the buffer allocated with malloc and so on. A DBI enabled to recover some of the original semantic of the program, but it only provides primitive, and you need to use this primitive to set up what you want to analyze. So for instance, if your code is dealing with memory access, you may want to have to set up memory access callback. Or if you know that it's just about getting an external call trace, you may just want to use the exec broker. So it depends on what you want to reverse. Also, one of the drawbacks of the commercial obfuscator is that usually the people that develop obfuscator are very talented in their field, and the developers are very talented to develop. But sometimes developers may not know very well how to use a specific obfuscation passes. And it can be like quite tricky because, for instance, if you don't encrypt string, it's quite straightforward to identify what is the purpose of function and so on. Also, I would like to thank Charles Huben and Cedric Tracy because they are the original author of QBDI, and I well, I would not be able to make this code without their initial work. Also, thanks to the LLVM community, because the LLVM framework is widely used in the security field. So we have Relic and Remil from Trados Bits, QBDI. We have also Haribo that were used with Triton to recover some kind of obfuscation also. We have Redec from Avast and OLLVM and most of the obfuscator now. Thanks to my colleague and Quartz, because I work in a very interesting environment in which I can do this kind of work and to explore this kind of topic. So thanks to them. And thank you for your attention. And now if you have questions, I'm free. Thank you.